we have learned in two-dimensional elements, we have these triangular types, right? Linear and quadrilateral types of linear and quadratics. Then in terms of 3D, we have tetra, hexa, linear, and both linear and quadratic types of elements, right? So today, we look into how we analyze, or how we formulate and first formulate and then analyze problems that involving two-dimensional and three-dimensional solid mechanics problems. Right. So back to what we call our mechanics of materials. Right. So to get what we call the general state of stress at a point in three dimensionals, then we have this sigma x, sigma y, sigma z, as well as the shear stress. We have tau xy, tau yz, and tau xx. Right. So if talking about plane stress situations, then basically this state of stress will reduce through only three components. So you have only sigma x, sigma y, and tau xy. Right. So later on, two-dimensional, particularly we are looking into plane stress situations when we have dealing with x and y directions of stress. So if you're talking about the strains, okay, if you have stress sigma x, sigma y, tau xy, then the state of strains, then epsilon x, y, z, and gamma x, y, y, z in three dimensionals. Okay, that is what we have. All right. So that is what we have in 3D. Right, three-dimensional general state of strains. Okay, at a point you have epsilon x, y, z, and gamma x, y, y, z, and x, z. Right, this epsilon, or what we call the strain, we learned before. It basically is the derivative of our displacement vectors or displacement field with respect to x, y, and z respectively. Right, so that is how it can be represented. Previously in one-dimensional, we are looking into this. Right, so now in let's say three-dimensional, then we have additional displacement vectors or field of v and w, representing the displacement in y direction and z directions. Right. So in terms of shearing strain, then we have this del u, del y, del u, del y plus del v, del x in shearing strain of x, y, y, z, basically del v, del z, del w, del y. X, z is del u, del z, del w, del x. All right. So that is a general state of strains at a point. Then in the case of plane strains, okay, then we have, of course, it will be reduced to only three. Yeah. So we again, same like plane stress, we do not have the z components all gone, right? So here we end up, we only have epsilon x, y, and gamma xy. All right. So that is what happened in under plane strain situations, right? So relationships, okay, between the state of stress and strains that we have also learned before, right? So so you could have epsilon x. Basically, you have also contribution from the stress, okay, normal stress of in x direction, as well as normal stress in y and so-called z directions in this case. Right. So probably can before I come back to here, probably can show you here under so-called isotropic material. So we know that our isotropics, maybe let me write it. Isotropic E is basically constant, basically equals to EX equals to EY equals to EZ. So then we know that in this case, our sigma X will cause uh, strains, sigma X, epsilon X over E. It will also cause a strain in Y, okay, where you have this new with our Poisson ratio. Okay, so we have negative. At the same time, when you have undergoing normal or what we call positive so-called strain or elongations, then we have also a negative in these transverse what we call directions, which have a negative. Okay, so you will have in the y directions, in x directions. Then we have also epsilon z. Okay. Sorry. So we will say that sigma x itself will cause what we call the strain in x, y, which is a negative, and z also is negative. Similarly, we have sigma y as well. We have okay, a negative epsilon y, which is a positive, right? Then z is negative, right? Okay, so sigma y will cause also this. Then we have sigma z will also cause 3 what we call steps, which is positive, negative, negative. All right, so basically this, if you sum all, okay, this plus this plus this, and for your epsilon x itself, then you have sigma x over E minus y over E minus sigma z over E. All right, so that is where you have, yeah, this one. All right, so y itself also the same, and also z itself also will have the similar effects. All right. Then of course, we have also our shear stress and shear strain itself. Basically, is governed by our shear modulus G itself. So we have a normal shear stress x y basically is G. Same with shear strain. So same with here, we have our sigma x equals to E in one direction, epsilon, right? X. But in this particular case, in three-dimensional state of stress, then our epsilon x is not purely by the x itself, sigma x itself, but also have some contribution from y and z itself. All right. So that basically give us the informations or the relationships between the stress and strain in three-dimensional. All right. Okay, so then we have also relationships of between the shear modulus that we have just now. This G and E itself. Okay, we also learned that it is equals to 2, 1 plus V. All right. So in this case, if I want to look into just plane stress itself, then where we only have the E epsilon x, y, and gamma x, y itself, then we only have a contribution from our epsilon x or strain in the x directions. Basically, we only have a contribution from a normal stress in x as well as y, no z directions, right? So similarly with y, normal strain in y also the same. You only have contribution from x and y, and just now we have also gamma xy, which is shearing strain itself. Basically, is a 1 over g. We have this, right? Sorry, we have this 1 over g, right? So this g itself is e 1 over g is 2 1 plus v over e, right? So we have 2 1 plus e over e tau xy. So that is in general our so-called in matrix forms. It can be represented our strain and stress. Right? Sometimes, okay, you have some initial strain. So that is our initial condition. If you have, if no, then that thing will become 0. So in general, basically our strain itself is E. Basically is what we call E inverse, or we call this inverse so-called stress, because usually we say stress equals to E strain. So this itself is what we call for a stress, plane stress. Okay, for plane stress, this is a E is a 3 times 3 matrix, right? Covering sigma x, sigma y, and tau xy. So if we want to express our stress, okay, in terms of strain, then rearrange it, then where we have this inverse E, okay, we find the inverse of this E itself, then multiply with this strain, that basically this invert, this is what we call our E itself, okay, of a plane stress components, right? So that is our E, can be represented by so in terms of plane stress, okay, plane stress, that is what you have seen here. So in terms of plane strains, all right. So for plane strain, so conditions are the normal stress, okay, sigma z is basically exists in addition to other three stress components. So what you have here under plane strain compared to plane stress itself, basically you have to consider we have to consider the contribution from the z, okay, sigma z, that is so basically no displacement in plane strain is that epsilon z is equal to 0, okay, only. So you have also epsilon x and epsilon y, which is normal strain and normal stress in terms of what we call from in terms of x direction and y direction. So you also have contribution from this is the normal stress of x, y, and z. Okay, so that is a little bit difference between plane stress uh, condition and plane strain condition. So where you have this what we call the z component coming in. So from what we have here, plane stress, sorry, plane stress that we have derived. So now the E under plane strains, this E basically is replaced by 1 over V square 1 minus v square, our nu, which is our Poisson ratio, basically replaced by v over 1 minus v. G still remain g. So in this case, our under plane strain conditions, so our this become our E inverse. Okay, so this is just now our E inverse, right? So this is our E inverse, the whole entire. So in the case of stress in terms of strain, that this particular now is our E. Okay, under plane strain itself, E is slightly different with our E in terms of stress, because this E now is replaced by what, E over 1 minus V squared. So if you look back into, let me show you this, the one that I have derived just now here, right? So if you are considering the Z itself, right? So under this so-called, we have this just now. Let me show you. So just now we have, let me use another colors. We have our under plane strains, right? So we have this, okay? Under plane stress, we do not have these parts, okay? Plane stress, this part is gone. No contribution from Z axis. So, okay? So, but under plane strain itself, epsilon Z is equal to 0, but we still have contribution from the normal stress in Z. So that is our plane strains so-called equations. All right. So in this case, if you refer back to this equation itself, so we have our sigma Z over E is actually equals to V sigma X over our new sigma X over E plus new sigma Y over E. All right. So if I want to find sigma new sigma Z over E, okay, this one, we want to include this component. So basically it's new square sigma X over E plus new square sigma Y over E. So if you combine them, okay, if we these things, okay, this we substitute into here, then our sigma X epsilon X is equal to sigma X over E minus sigma Y over E. Then we have also minus V square sigma X over E minus new square sigma Y over E. Right, this new is our Poisson ratios. All right, so basically that gives us what we want, or 1 minus new square over E sigma X, then minus V new 1 plus new over E sigma Y. Right, so that is why we say that now our under plane strain itself, our E become, okay, this our E now become E over 1, basically this part, sorry, here, right? Basically is this, and our new over E basically now is becoming this. Okay, our new is B, new plus multiply with 1 plus new. So that is under plane strain. We say that our E now become E over 1 minus new square, 1 minus new square, then new basically now equals to new over 1 minus new. Okay, so that is what we have. Right, so that is what we have done with this. This is 1 minus, if you see that we have 1 minus nu square. Then we have this nu minus nu square. So this is yeah, correct. Okay, so that is what we have under plane strain. So basically that is the relationships on our what you call the stress and strain relationships. Okay, so under plane stress condition and plane strain conditions. So this is important. So later on to help us to formulate our solid mechanic problems. Okay, so if we know this so-called epsilons, okay, itself, right? So under this stress plane, sorry. Okay, under plane stress conditions, that this is what we have, right? So some books they use this, but here we are using this itself is our so-called E. Okay, it can be called our E. So stress under plane strain condition, also this we sometimes is used new. Basically, it's just a symbol representing the material properties or Young material properties in terms of Young modulus as well as Poisson ratio that representing the relationship between the stress and strain components. All right. So here, so if we can find the stress strains, we can build the stress and strains relationships, right? So then, of course, we can also find from the strain itself. We also have the strain and displacement relationships. Okay, del U, del X. Under plane stress situations, del V, del Y, del U, del Y plus del V, del X is your shearing strain X, Y. So with this relationship again, then we can making use of these strains later on with the energy methods to formulate a problem of solid mechanic problems, right? So this is relationship. So in other way, we can also write epsilon x, epsilon y, gamma xy in terms of matrix form. Basically, is del u, del x, del v, del y, right? And del u, del y plus del v, del x. Basically, you can represent in these particular forms. All right. So how we want to formulate, right? What we call the problem, okay, of the solid mechanic problems using what we have derived from here, plane stress conditions, right? So here we can, of course, we learn before, okay, under two dimensionals, we learn two types of elements. We learn two types of elements here, okay. We have triangular and quadrilateral, both linear and quadratics, right? So linear, triangular. So sometimes, okay, you will see it's actually called constant strain triangles, okay, CST. So linear triangular element sometimes is named as CST or T3. We know that a linear triangular we have 3 nodes, right? Quadratic triangular we have 6 nodes. So sometimes we call T3 triangular 3 or triangular 6 for quadratic. So another name is CST and LST. So it's a linear triangular element is a constant strain. So later on when we represent them in the strains, formulate them in terms of strains, then you will see that it's actually the strain is actually constant in terms under these linear triangular elements if you are using linear triangular. If you are using quadratic triangular elements, so you have a linear function of strain, then that sometimes is called LST. So these two names are very common, but they are referring to the CST referring to the linear triangular, LST is referring to quadratic triangular. Just another name. Then we have also quadrilaterals, okay, linear rectangular elements, and also quadratic Q4 and Q8. So again, repeat back what we have discussed last week. Linear, okay, Q4 or T3 is a linear elements. Q8 and Q8 and T6 are basically quadratics. Then good for linear is good for deformations. Then quadratic is good for stress. All right. So how we look into this particularly what we call CST, okay, what we call linear triangular element, called a strain triangle. Right. So recap back what we have discussed under during these two-dimensional elements. So we have under displacement variable itself, two-dimensional. Of course, I mean this is 3 nodes, so we have components, a displacement component in terms of two directions, x and y direction. So here we represent by u. In terms of its shape functions, basically it's SI, UI, SJ, UJ, SK, UK. In terms of its x directions, then we have V representing the y direction, SI, UI, SJ, UJ, and SK, UK. So if we want to represent in a matrix form, then probably this you'll see that our UV itself basically is SI, right? UI, SJ, UJ, SK, UK. Then we have V is SI, UI, Y, right? SJ, UJY, and SK, UKY, right? So another forms, okay, it can be also represented in terms of sometimes the shape function is represented by N, 1, 2, 3, also the same. So, okay, you have N1, U1, N2, U2, N3, U3, okay. Then we have also N1, you can say U1Y, U1X, or you can use straight away V representing the displacement in Y direction, U representing the displacement in terms of X directions. Then you have this N2, V2, N3, V3. So that basically is what we commonly know, okay, in terms of two displacement vectors U and V in terms of its shape functions. Right, so three linear triangular element, you have three nodes, right? So you have three shape functions. So in terms, if you are representing in matrix form, then you basically also three shape functions. Then you have these 2 times 6, okay? Three shape function in terms of x and y. So 2 times 6, then this is 6 times 1. So basically you get this UV. All right. So recap back the shape functions that we have derived, okay, last 2 weeks under linear triangular elements. That is our 3 shape functions that we have. Okay. Right. So in other words, okay, you can represent in N, like that is another book, they use N1, okay, so it can be represented like this. So again, you have this, if you look at this, our I, J, K basically representing at here is 1, 2, node 1, 2, and 3. Okay, node I, J, K, you can represent at node 1, 2, 3. Right? So you have Yj minus Yk basically is representing Y2 minus Y3. Basically is your Yj minus Yk. Okay, so they are equal. Right, so in other words, I mean, it can also represented by this Y2 minus Y3. Basically, you can later on be written as Y23. Okay, Y2 minus Y3, you can simplify is Y23. So similarly with this Y J K. Okay, so it can be simplified. So if, okay, the shape functions is there, 3 shape functions that is given. So if we want to find epsilon, what we call our strain x in x, strain in normal strain in x, normal strain y, and strain xy. So that is what the relationships that we have, this strain and displacement relationship that we have discussed just now. Sorry. Here, making use of this Okay, so if we can rearrange them against, okay, in terms of our displacement form in terms of its shape functions. So del u, del x, del v, del y, and del u, del y plus del v, del x, right? So basically, you are finding the derivative of our displacement field, okay, u, with respect to x, okay? So here, our shape function is a function of our x, y, right? So basically, it's finding the derivative of our shape functions. So if you find our derivative of a shape function, del s, okay, I del x, okay, or you have del, basically you have this beta I, right, equals to beta I. All right. Can you see that here? So here, basically, you give you the beta I at here, right? So if you are having del s I del y, then you have this delta I. All right. So similarly, we have del sj, del sj, del x. You have beta also, but it's beta j. Then del sj, del y is delta j. Okay. So similarly, we have del s k, del x is beta k, del sk del y equals to delta k, right? So if you have this information, then you can actually see that your epsilon x, epsilon y, and what we call the shearing strength xy itself can be written as this, okay? All right, can be written as this, can be simplified as this, making use of the derivative of our shape functions with respect to with reference to x and y. Right. So in terms of matrix forms, right? So our epsilon x, normal stress, normal strain x, normal strain y, and tau, what we call this shearing strain xy, it can be represented in terms of matrix, which is this 3 times 6 and 6 times 1. Okay, so that basically give you which one node, node 1, node 2, and node 3 in terms of x and y. Right, so you can represent this epsilon equals to bu itself. All right, so in the other way, also the same. I mean, if you are having in terms of n1, n2, n3, also the same. You are getting our relationship of epsilon equals to b. So called this d itself is basically is our u1, v not 1, u2, v2, and u3, v3. So y23 basically is referring to our beta. Basically, this is also a beta I, beta j, beta k. So y23 is what we have here is y2 minus y3. This is y3 minus y3 minus y1. This is y1 minus y2, right? So it's similarly with this. So same, if you can see this, our y23, our beta I here is y2 minus y3, y3 minus y1, okay? Yk minus yi is y3 minus y1. This is y1 minus y2 is our beta k. So it can be rearranged at the same form. So here, our strains, you can see that is actually a constant values. So you see that it's not a function of x, it's not a function of y, because it have been previously our shape function is a function of x and function of y, right? But the strain itself is a derivative of a shape function, making use of the derivative of the shape function. Then our strain itself, this is our strain itself, is a constant value. Okay, so it's a constant strain, what we call triangle in this case. All right. So this is a constant strain within the element itself. I mean, our this our beta, our delta, delta, all are the constant values. Okay, so meaning our strain is a constant strains. Right. So if you have strains, right? So if you still remember, we how we making use of the energy methods. So if you have the strains, then we can making use of the strain energies. Okay. Then from the strain energy itself, we find the minimum total potential energies. Basically is the difference between the minimum strain energies. Okay. Difference between the minimum strain energies with the work done by the external loads. So that is our minimum total potential energies methods. Okay, the energy method that we have used. Right. So in one dimensionals, right? So we have our strain energy. If you still remember, basically is equals to uh, stress strains dV, right? So in, let's say now we are having plane stress under 2D, two-dimensional, then we have sigma xx epsilon xx, then we have to also add the y direction, and also we have to add again the shearing, what we call strains, stress and shearing strains, right? So that basically give us, okay, or it can be simplified in terms of in terms of matrix. Basically is will be like that. Or so we have our x y y or x y, okay, multiplied with our our x y y and x y. Okay, so it can be represented in terms of this. All right, then if you still remember, okay, we have also our stress itself. Just now our stress itself is in terms of matrix. We have this uh, E epsilons. So this E itself is a 3x3 matrix, right? Then, or what we call here is a new, also the same, just a symbol used representing this itself. So this is 3 times 1, this is 3 times 1. So in this case, our stress itself can be represented by this transpose, okay? So and expand it, it becomes transpose, our epsilon transpose, and then our E transpose, or new transpose, okay? So the entire so-called strain energy now become this, okay? Then we know that our strain itself just now, right? Our strain itself equals to BU, okay? Our strain itself equals to BU, where is in terms of our strain in terms of displacements with the constant constant strain itself, our derivative of a shape function itself. So now it basically give you this itself is BU, right? So the transpose basically is U transpose B transpose. All right. So that basically give us our strain energies. Okay. At the same time, if you are in the other forms, right? So basically, this itself is our V. So basically, we have also this new itself now in another form we represented by E. So basically, you also get the similar results. Basically, you get this, okay, this thing. All right. Then with the strain energies, okay, the total potential energy is the difference between the total strain energy and the work done by the external force. Okay, so this is what we have previously. So if you want to find the minimum total potential energy, then basically you find the derivative equal to 0, right? Then that part is our minimum total strain energy. This is our minimum, what we call the work done by the external force. Then we have this minimum total potential energy. All right. So you find the derivative of our so-called strain energy that we have derived from here. All right. So if you find the derivative with respect to its u, okay, then basically that is the nodal displacement. So that is what we have. I mean, you still remember uh, we discussed before in X beam itself, or X beam or axial member itself. This, okay, can be simplified into what we call, you see the derivative itself, this thing, okay, if you find out, if you still remember, so d del uk, this what we call, we have learned this in term in what we call during, I think, beams. Let me open and show you, right? Strain energy is equal to this, right? So if we are finding the derivative of it, then basically this 1 over 2 u transpose itself, basically it will be gone. Basically end up, if you're finding the derivative, this part will be gone. Basically end up this u. Okay, so we know that this itself minimum strain, so-called energies, total strain energies is Ku, right? We know that's Ku minus F, okay, equal to 0. So this is basically itself is our K. So if you can rearrange these things, okay, we have this 1 over 2, right? 1 over 2 U T itself, okay, will be removed later on. Then we have this B D, then V or E, I mean nu or E are also the same. Then B itself, dV, then we have this U. So this itself is our K, then we have U itself, if we find this, right? So this particular part will be limited. So here, the stiffness matrix, we know that is basically given by this. All right. So basically, it's the volumes of the elements and multiply with this B transpose E, our so-called our what we call the material properties in terms of Young modulus, as well as our Poisson ratios that we have derived just now under plane stress, okay, conditions, and multiply with this B itself. Okay, so just now we have determines this so-called B is a 3 times 6 matrix. So B itself is a 3 times 6, okay, matrix. So our new, or what we call our ER metric properties is under plane stress is 3 times 3, right? So the transpose is 6 times 3. So end up we have 6 times 6 K. Okay, so basically is basically is correct lah, or what we are saying that we have under these linear triangular elements, we have 3 nodes, okay, then under we have 3 node itself, then under 2 directions in terms of x and y, then we have total of 6 in this case. So here we are talking about one element itself. We have 6 so-called three nodes. Each node we have 2 degrees of freedoms. Then total our stiffness matrix will be a 6 times 6 matrix. Basically, it's 3 times 2. Okay, so our stiffness matrix is a 6 times 6 matrix for a linear triangular element, or what we call here constant strains triangle. All right, so that is making use of the shape functions in terms of the what we call global coordinates. So we also learned that in our linear triangle element in terms of its natural coordinates. We have this psi, eta, and also lambda, right? So if in this particular case, okay, in this so-called natural coordinates, then we can use this isoparametric linear triangular element to derive the what we call the stiffness matrix. Okay, so here, if you're looking into what we call isoparametric linear triangle elements, we have discussed also before, okay, where we can from here we can derive also or formulate also the what we call the stiffness matrix. So if that is the case, right? So we have our shape functions, which is in terms of if natural coordinate, we have this n shape function 1, okay, or n1 is psi, n2 is eta, then n3 is lambda, which is equals to 1 minus psi minus eta, right? So in terms of its displacement field, okay, we have this u equals to S. Previously, you can put S1 U1 plus S2 U2 plus S3 U3, or now you can put equals to N1 U1 plus N2 U2 plus N3 U3. So similarly, we have V is S1 V1 plus S2 V2 plus S3 V3, or N1 V1 plus N2 V2 plus N3 V3. All right, so that in matrix form, that basically gives us this. All right, so under isoparametric formulation, or under isoparametric elements, right, we are saying that the displacement field, okay, basically, and also the geometry field of is basically sharing the same shape functions, right? So again, our x and y in terms is the position of the elements. It's also sharing the same shape functions, n1, n2, n3. So it can be written as what you have seen here, okay? n1 x1 plus n2 s2 plus n3 x3. Y equals to n1 y1 plus n2 y2 and n3 y3. All right, so in this particular case, okay, because our n3 is 1 minus psi minus eta, right? So now if our x now is equals to n1, okay, basically is our psi x1 plus eta x2 plus here we have x3 minus psi x3 minus eta x3, right? So here itself, you can have this psi x1 minus x3 plus eta x2 minus x3 plus x3. All right, so here basically is x1 minus x3 x1 3 psi plus x2 3 eta plus x3. So similarly, for y itself also it will have this, right? For u itself also the same, okay? for u itself, this is u, this x. For our u itself, we also have psi u1, u13, right, plus eta u23 plus u3. Okay, so that is in terms of u displacement. This is in terms of our x. So y also the same, v also the same, right? So that basically give us they are sharing the same shape function under Isotropic Matrix, right? So making use of the chain rule as well as the strain and what we call displacement relationship. So we have del u, del psi, del u, del eta only, okay, equals to making use of the chain rules that we have. Basically is del x, okay, del u, del psi equals to del x, del psi, del u, del x plus del y, del psi, del u, del y. Okay, so that is the first. From here, multiply this plus this, multiply this. All right. Del u, del x. So basically, you give you del u, del psi. So similarly, if you have del u, del eta, so also the same del x here to here, okay, and here to here, right? Del x, del eta, del u, del x, right? Plus del y, del eta, del u, del y. So for the v component, also the same, del v, del psi, del v, del eta. So here we are saying that this is this 2 times 2 matrix here is basically our J or Jacobian matrix. Okay, right? So if you want to find del u, del x, okay, now we have the relationships of del u, del psi, del u, del eta equals to j del u, del x, del u, del y. So this is what we want, right? Del u, del x, del u, del y, which is given us the later on the strains. So rearrange it, then we have the inverse of it. So that basically gives us an inverse of a Jacobian matrix, transformation matrix. Then basically that give us this. Okay, so uh, if you look into this del u, basically from where I can draw it here, del x, del psi, from here, del x, del psi, basically if you're looking into here itself just now, okay, del x, del psi basically is, right, del x, del psi equals to x13, right? So if you have del x, del eta, we have x23. Similarly, if you are having del what we call y itself is also the same. So if you have del y, del psi equals to 1, y13, del y, del eta equals to y23, right? So here basically give us our Jacobian x13, y13, x23, y23, which is x1 minus x3, y1 minus y3, x2 minus x3, and y2 minus y3. So getting the inverse itself, yeah, basically is equals to basically this swap y, then this one negative, you will get this particular part multiplied with divide by the determinant of the j. So determinant of the J itself, okay, determinant of J itself is actually what we have here is x13, y23 minus x23, y13. So it's actually, if you compare back to what we have learned previously, is actually equals to the 2 times our area of our so-called triangle. All right. So with this, we have del u del x equals to del u del y, del v del x, del v del y. Okay, in terms of our so-called inverse Jacobian matrix, and also del u del. Same with this, del u del psi, del u del eta. Here is giving us u13, right? So this del u23, right? So for del v del psi del v del eta, we have a y13, sorry, v13 and v23. So that basically gives us this. Okay, so that is this one, this is this one. All right, so combining them, expand them, okay, in the forms of this, okay, epsilon x, epsilon y, and gamma xy itself, then we have this particularly del u del x del v del v del y del u del y plus del v del x, okay, equals to what we have. We just rearrange everything, okay, that this particular part del u del x, we have a y 1 over 2a, okay, y23, here negative 1y3, I can write 131, right? So in terms of, we have to write in terms of u1 v1 u3 nodes, u2 v2 and u3 v3. Okay, so that basically gives us our 6 times 1 matrix. Okay, this is our 3 times 1 matrix. Then we know that our so-called 3 times 6 itself is our B. Okay, our B U, that gives us the epsilon. Okay, our string informations. Right. So we have y23, y31s. Then we also have here is 0, y12, 0. Right. So that is related to our so-called what we call, you see this our y here, y23, y31 to u2 and u3. Then we have also u2, y3, we have both itself. Okay, y23, okay, basically is y 23 negative u3, right? Then we have also here negative 1y3, here negative u3. So basically it is representing by y, in this case is y. Sorry. So in this case is y 3, 2 minus y 3, 1, right? So here it is representing, here is y12 lah. Basically simplified to that is y12. So similarly, you have for del v del y also the same as 0 x3 to 0 x13 0 x21. Then finally we have this del u del y plus del v del x. We have this x32 y23 x1 y31 x21 and y12. Right, so basically that gives us what we have derived just now, right? Our so-called B matrix, which is equals to 3 times 6 matrix. All right. So if that is using ISO parametrics methods, basically they are sharing the same shape function under this natural coordinates. So making use of these isoparametrics, so-called formulations to formulate what we call our strains in terms of displacement del u del x, del v del y, del u del y plus del v del x itself. All right. So if we have determined the similar B itself, B matrix, then the K itself that we have determined just now is a B. Basically making use back the energy methods or whichever. We know that our K Stiffness matrix is this 6 times 3 times 3, which is what we have here. If you still remember, our E itself is this, right? For plane stress, then our B is 3 times 6. Then we have our so-called stiffness matrix is 6 times 6 matrix. All right. So constant strain triangle CST, okay. Basically it is used I mean linear, right? It's a linear triangular elements, right? So used when area the strain gradient is smaller. Basically you don't have any changes of strains, then basically you can use it. Also we avoid using this CST or linear, as I mentioned, and you are dealing with stress, okay, especially you have stress concentrations, okay, but usually it's used for a quick preliminary FE analysis when we are dealing with linear elements, okay. That is what we have discussed before. So next is linear strains triangular or LST. Here is referring to quadratic triangular elements. So under quadratic triangle elements, you have found that is actually the strain is actually a linear function. It's not a constant, okay, because it's another higher orders. Okay, so if you look into this, we have also derived previously our T is A1 plus A2x plus A3y plus A4x squared plus A5xy plus A6y squared. Right. So in terms of displacement field, U and V, basically it also represented by as you have seen here. Okay. So the strains itself, okay, basically is del U. If you can find, remember that our strain itself is del U, del X, del V, del Y. This is del U, del Y plus del V, del X, right? So if you find del U, del X, then you have this B2, right? 2B4X, B5Y, right? So you will see that is a linear function. Similarly with this, okay, it's a function of x and y. So here we are saying that under what we call if we are using quadratic triangular elements, then we are actually saying that this is a linear strain triangle or LST. Okay, so of course higher order is providing better results than CST. So this is another name lah, basically. Oh, so if you are using, just remember you have 6 nodes, so under the shape, 6 shape functions, so in terms of its natural coordinates, that is we have derived before, okay? If you see something similar like this, okay? So can refer back that we have derived, okay, in terms of psi, eta, and lambda. So, or in terms of psi and eta itself, okay, so it can be simplified as you have seen here or here, okay, interval n1 and 2. So under isoparametric elements, so we know that our displacement field, okay, using the straight functions as you have seen here, we have displacement field can be represented by this as well as our geometries. So we have our u v equals to n1 6 node, n2 n3 n4 n50 n60, right? So this is our n1 n2 n3 n4 n5 n6, right? So here is referring to u1 v1 u2 v2 until u6 v6, right? So here is referring to 12 times 1, 2 times 12. Okay, so similarly, our x and y also the same. We have our x equals to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4 plus n5 x5 and 6 at x6, right? So y is also the same, and 1, because they are sharing the same shape functions, y1 plus n2 y2 plus n3 y3 plus n4 y4 plus n5 y5. Right. So in the matrix form, basically you can also represent that by as you have seen here, x, y, 1, 2, and 3, and 4, and 5, 6, 0, and 1, 2, 3, and 4, 5, and 6. Right, so you have this x1, y1, x2, y2 until x6, y6. So its positions. All right. Then we making use of this, the rules as we have seen here, right? So again, here basically become our Jacobian transformation matrix. So it can be represented by this, let's say J11, J21, J12, J22. All right. So in this case, you have del u, del x, del u, del y. Basically, is just the inverse of this Jacobian transformation matrix multiplied with del u, del psi, del u, del eta. So everything's similar. You will see that you have the del u, del x, del u, del y, as well as later on we have this del v, del x, del v, del y. Right? Also the same J inverse, del v, del psi, del v, del eta. All right. So if we can find this, okay, basically is from these two. Here we can get our del u, okay, del psi, okay, del u, del eta, del v, del psi, del v, del eta. So from here we can find our del x, del psi, del x, del eta, del y, del psi, del y, del eta. So from here, we can find our del u, del x, and del u, del y, del v, del x, and del v, del y. All right. So from what we have here, so you rearrange them, okay, in terms of del u, del x, del v, del y, del u, del y plus del v, del x. Then basically it determines here you have just now similarly we have this 3 times 4, which is referring to the what we call two shape functions, psi and eta. Okay, so and also 3 times 4, then we have here is 4 times our 12. Okay, 6 nodes. Okay, in terms of x and y, so we have total of 12. So here basically we have del u. If you are looking into here, so if I can expand del u, del you have del u, del psi, you have it del v, del u, del psi. So this is v, del u, del for node 1 itself. This is node 1, okay, u and v. Then you have node 2, u and v, okay. Then you have 3, u and v, 4, u and v, 5, 6, right? So basically it's a non-zero, 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 right? So similarly, we have del u, del eta, also the same. You have a non-zero, zero, non-zero, zero, non-zero, zero, right? So a total of 12, okay? 4 times 12 matrix. So here, del v, del psi, then you have 0, non-zero, okay? 0, non-zero, 0, non-zero, 0, non-zero. Right, so I don't go and derive all, okay? Differentiate all for you. Okay, so basically that gives us a 4 times 12 matrix, okay, in terms of full matrix, in terms of del u, the derivative of our so-called displacement field with respect to its shape, the shape functions here is referring to psi and eta. Okay, so we have 4 row so-called 12 column covering the 6 nodes. All right, so end up we have 3 times 12 so-called of this itself is our B, if you still remember. So B, U basically give us our epsilon. All right, so that our B is so-called 3 times 12 matrix. Huh? All right, so if we have this 12 times 3, our E itself, material properties is still 3 times 3, then 3 times 12, then we have our stiffness matrix here is referring to 12 times 12 matrix. All right, so our stiffness matrix here is a 12 times 12 matrix, basically referring to our 6 nodes, okay, in 2 directions. So 2 degree, each node have 2 degrees of freedoms, then total of 12 times 12 matrix. Right, so that is LSD. So we covered triangular elements, linear and quadratics. Linear is called CSD, quadratic is called LSD. Then how it's being formulated to determine our stiffness matrix using what we call the energy methods. So here from 6 times 6 matrix, right? under CST or linear triangular elements. Now we under quadratic triangular element or LST, we have 12 times 12 matrix. So if you are looking into a linear quadrilateral elements, also the same lah. So in terms of the shape functions, in terms of the natural coordinates, psi and eta, right? So your displacement field as well as the position, or what we call the geometry, basically is represented by using the same shape function can be represented by, as you've seen here. So quadrilateral linear quadrilateral elements is a total of 4 nodes. So you have a U1 V1, U2 V2, U3 V3, and U4 V4. So similarly, we have X1 Y1, X2 Y2, X3 Y3, and X4 Y4. So that is referring to 4 nodes, 4 shape function, N1, N2, N3, N4, N1, N2, N3, N4. All right. So making use of this again, so the isoparametrics. We have our so-called Jacobians, which is referring to what you have seen here, del X, del psi. So here, from here, we can find our del U, del psi, del U, del eta. Then we can find del V, del psi, del V, del eta. Same with here, we have del X, del psi, del X, del eta. We have del, we can find also from here is del Y, del psi, del Y, del eta. Right? So from here, we can determine this, and this. Right? So if we can determine this for all these two, then we can find our del U, del X, del U, del Y, as well as del V, del X, del V, del Y. So from there itself, we can find our strains, okay, epsilon X, epsilon Y, and also gamma XY. Yeah, the whole I mean the procedure is still the same and the isoparametrics. So just that now previously we have 3 nodes, 6 nodes. Now under this linear quadrilateral element, we have 4 nodes itself. So here we rearrange them. Then we have this against 3 times 4 matrix, right? So for here itself, we have a 4 times 8 matrix, basically referring to here is del U, del U, del psi for first nodes. We have this node 1, node 2, node 3, node 4. We have both U, V, UV, UV, UV. So del U, del psi itself, you have this non-zero, zero, non-zero, right? Then you have also del U, del eta, also non-zero, zero, non-zero, okay? Then you have del V, del psi is zero, non-zero, zero, non-zero. So same with del V, del eta. Right? So here basically give us a 4 times 8 matrix. So 3 times 4, 4 times 8, basically it gives us our epsilon equals to B U itself, right? So this B itself is a 3 times 8 matrix. Right? So if you have this 3 times 8 matrix, okay, so basically if you can see the full derivations of this, so that is what I written for you. Okay, it's a 4 times 8 matrix, 3 times 4 matrix. Then here is 3 times 8 matrix. So 8 times 3, our E matrix property is the same, 3 times 3, then 3 times 8. Then we have our stiffness matrix here is referring to 8 times 8. Okay, basically you have 4 nodes times 2 directions, or 2 degree of freedom. Okay, so we have a 8 times 8 matrix in this case. All right, so that is how we derive our stiffness matrix in 2-dimensional elements. So we have, if you still remember just now, we have this under the minimum total potential energy equations, we have K U, right, minus F equal to 0. So K, we know if we are using CST, LST, or quadrilateral. So basically, we know that how to derive this K. Then F itself, if we can determine also like what in 1-dimensional, if we can derive the F itself, then basically we can solve the problems, the solid mechanic problem in 2 dimensionals. All right, so under the load itself, if you have concentrated load, of course, basically your Q, okay, you can represent it by F, your matrix, F E itself. Then basically you have a Q1X, Q1Y, Q2X, Q2Y, until depends on how many nodes you have. I mean, what element that you are using, okay? If you are having a concentrated loads, right? So it basically applying at the nodes itself, right? So if you have three, if you are using a linear triangular, okay, then you have 3 nodes, then you have Q1X, Q1Y, Q2X, Q2Y, Q3X, Q3Y, okay, applying the nodal force at the node itself. Okay, so if you are having, this is your Q itself is your nodal force, okay, multiply with the U, and that displacement itself, that basically is our work done. That is what we have derived previously. So if you have a distributed load, P, okay, along x-axis, Y along P along y-axis, then basically you have this, you can represent your work done, basically is U Px V Py. Okay, U is displacement in X, V is displacement in Y. So if that is the case, right, our work done itself, you can represent our U. You still remember our U and V is basically is the shape function multiplied with U and V itself. So this thing can be represented by our work done in one element itself if it's distributed. So we have this SU T, right, P itself, dA. Then we have SUT is UT ST P. So that basically gives us our so-called work done. So if it's talking about the load itself, right? So then that is work done, right? So if you're talking about the load itself, just the force, the nodal force itself, then basically is this particular part only. So this thing coming out, displacement coming out, then you see this is equal to your Q. So if coming out this itself, U D, then you have this S P D A. So this itself is our Q, okay, for distributed loads. So for this concentrated load, that is given. So for distributed load itself, then F elements or element load matrix itself is given by the transpose of a shape matrix, the shape functions, as you have seen here. Okay, is our shape function just now. If you are using a linear triangular, I mean, talking about, for example, we are using a linear triangular elements. So it's 3 nodes itself, right? So we have our shape functions. S itself is S1 0, S2 0, S3 0, 0, S1 0, S2 0, S3. right? The transpose is basically you rearrange in terms of this form. Okay, so if you have an element subjected to a distributed load along, let's say K, if let's say this is a triangular element, a linear triangular element, 3 nodes, right? So if it's along Ki, along the Ki, you have a distributed load itself, then basically you have the shape function multiplied with Px and Py, okay, dA. So if you are expanding, this is what we have here, St, okay? So if you are expanding this, as you can see here, then under K and I itself, okay, the shape functions J is under this line, shape function J is 0, okay? So this can be simplified in terms of Si, Sk, and Sk only. So this particularly is 0 in this case. Multiply Px, Py, then the area itself, which is TL, okay, the thickness of this element multiplied with the what we call the length of Ik, okay, so that is basically our A. So A over 2, okay, Px, Py, that basically give us our so-called nodal loads in each what we call load matrix in each node itself. So if you have only your distributor along IJH, okay, IJ which is here itself, okay, if let's say applying at here, then you have only Px, Py, basically is no, this particular part is 0, Sk and Sk will be 0, right? So if you are in JKH, then basically you have Si equal to 0, right? So that give Si equal to 0, Sj equals to 1, Sk equals to 1. Sk, this is Sk equal to Si equals to 1, Sj equals to 1. Similarly with this, Si equals to 1, Sk equals to 1, Sj equals to 0. So that gives us what we have here. All right. So that is two-dimensional. Okay, if you want to determine the K, if we can determine the K, we determine the U, and we can determine the F, then we can determine solve to get our displacement. So for three-dimensional, of course, it's a bigger size. You will see this. It is at a bigger size. Okay, so under three-dimensional, then basically we consider all sigma x, sigma y, sigma z, tau xy, tau yz, tau zx, right? So from just now, 3 times 3, our so-called E itself is a 3 times 3 matrix. Then now this thing is what we call 6 times 6 matrix. Okay, so that is the 6 times 6 matrix. So our displacement field also the same, U1, U2, U3, basically representing by U, UV and W, U representing the U directions, in X direction, displacement X, V in Y, and W in Z. Basically, we are in three-dimensional, not only UV, but UVW, or we call U1, V1, U1, U2, and U3. All right. So in terms of strain and also the displacement field, so beside just now in under plane stress, we are looking into these two plus this, right? So now we have to include all total of all state of stress, epsilon z, so shearing strain yz, shearing strain xz. Okay, so total of 6 components. So under this, what we call if you are using what we call here, for example, we are using the hexahedral elements, 8 nodes, right? So if we are using hexahedral, then we have this so-called, yeah. Okay, so basically our shape functions you can represented by a U, V, W shape functions depends on how many nodes you have lah, how many which type of element that we are using. You are using what we call tetra or hexa, then it's up to us. Okay, the shape function, what is the size of the shape functions? Okay, so if we are using, for example, these linear hexahedrals, okay, we have total of linear hexahedral. Basically, is the what we call cube, or what we call here 8 nodes. Okay, hexahedral element. So the displacement wise, in terms of the shape functions, that is what, like what we have said, is a u equals to n1 plus n1 u1 n2 u2 n3 u2 3. So basically you have this what we call u equals to our shape function in terms of metric forms. We have n1 0 0, then we have n2 0 0 u v w. So n3 0 0, and we have until n8 0 0, right? So here we have 0 n1 0 0 n2 0 0 n3 0 until 0 n8 0. So w 0 0 n1 0 0 n2 0 0 n3 until 0 0 n8. So that basically is our shape functions having a total of 3 times 24 of size. Right. So similarly, we have our XYZ also the same under parametrics, right? So in the natural coordinate systems, we have also derived before. I mean, last week I have show you. Okay, we have total of 8 shape functions, 8 nodes, 8 shape functions, right? So using from here itself, we can find del u, okay, del psi, del u, del eta, del u, del zeta, right? Then we have also del v, del psi, del v, del eta, del v, del zeta, right? So del w, del psi, del w, del eta, del w, del zeta. So similarly, I mean, here we have also can find del x, del psi, del x, del eta, del x, del zeta, del y, del psi, del y, del eta, del y, del zeta, del z, right? Sorry, del z. From here, all we can determine because they are sharing the same shape functions, like what we have discussed just now. Del zeta. So from here, this can be determined. The Jacobian matrix also can be determined, right? So we can find the relationship of this. right? As well as del V, del X, del V, del Y, del V, del Z, okay, equals to J inverse del V, del psi, del V, del eta, del V, del zeta. So similarly, we have also del W, del X, del W, del Y, del W, del Z, right? Which is what we want to determine this, right? We want to determine these 6 terms, right? So here we have equals to J inverse again del W, del psi, del W, del eta, and del W, del zeta. All right, so if we can determine this, then probably we can have what we call here is our total of that J itself. Basically, this is our B. Okay, U. Okay, so this B itself basically is arranging what we have here. So is the J itself. Okay, so we have 6 times 9. So this B itself, B is 6 times 9 multiply with 9 times 24. Okay, so we have del U, del psi, del U, del ta, del U, del zeta. Let me. This B itself multiplied with U. Okay, that basically gives us 12. Here is referring to 6 is 24 times 1. All right, so here we will be having here our inverse of our J itself, inverse of our J. Okay, inverse of our J multiply with here is referring to del U, del psi, del U, del eta, del U, del zeta, del V, del psi, del V, del eta, del V, del zeta, del W, del psi, del W, del eta, del W, del zeta. So here, referring to 9 times 24 here. So total of 8 nodes. Okay, 3 directions. Okay, so we have here is referring to what you can see here later on. Probably I can del U, del psi, del U. Basically, you have node 1 until node 8 itself. I want to show you. So here itself, J 6 times 9, basically referring to here. Okay, 6. Okay, del U, right? So here probably you have 6 times 9. So basically this is a non-zero J 0, 0, 0, 0, 0, 0, okay, which is not non-related to this is related to del U del X, right? So not related to what we call here referring to only U lah, the V all gone, right? So next you have here right, then the third one referring to W, right? So at the same time, we have the fourth one is V and V and U itself. Then here we have okay, so we have also here 0, 0, 0. So basically that gives us our 6 times 9 matrix. So multiply with this our del U. This one is basically referring to del U, the psi. We have a total of 8 nodes. Okay, so we have here is 9, total of 9 so-called difference, 3 difference of natural coordinates. So here we have each of them we have we can write it as 1 times 24 lah. Oh, so it's basically 1 non-zero 0 0 non for node 2 is non-zero 0 0 until 8 lah. So 8 node itself, so this total of 24. So same with here. Right. So same with here. Then here will be 0 non-zero 0 0 non-zero 0 until 8 times. Okay, 24. So same. Then here is 0 0 non-zero 0 0 non-zero 8 times. Okay, so end up we have a 1 times 9 times 24 matrix. So 6 times 9, 9 times 24. Our B is basically we are referring to 6 times 24 is our B. Okay. Then findings, if you have this 6 times 20, our E here is referring to 6 times 6. 6 times 24. This is 24 times 6. Transpose is 24 times 6. Then end up we have our stiffness matrix is a 24 times 24 matrix. Right. So here is referring to linear hexa. We have 8 nodes, right? With 3 in 3 directions. So we have 24 times 24 matrix. Our K element for one element is talking about 24 times 24 matrix. All right. So that is one of the examples. Again, basically it follow the same. It can be formulated using the same isoparametric methods. So we have demonstrated, I mean, from 2-dimensionals using linear triangular element to quadratic triangle elements, or so-called LST, then to linear quadrilateral elements, then now towards 3-dimensional linear hexahedral elements, where it can be all formulated using isoparametric methods. And yeah, the size of it will be much more larger in 3-dimensionals because you are looking into 3 what we call directions. Then for each node you have 3 degrees of freedoms. All right, so that is some theories behind on solid mechanics problems lah. So under two-dimensional and three-dimensional. So we have covered one-dimensional in the very beginning of this course. Then now, after we have covered two-dimensional elements, the types, three-dimensional elements, the types of the elements, then now today we are looking into how it can be formulated, okay, to solve two-dimensional and three-dimensional solid mechanics problems.